A spark coil will take a low DC voltage and generate a very high voltage, high enough to result in dielectric breakdown of the air. In the 1800s, these were referred to as Ruhmkorff coils after Heinrich Ruhmkorff, although they were first developed by Nicholas Kellen in 1836. These Ruhmkorff coils were classified by the distance over which you could get dielectric breakdown. For instance, I found one which was a 42-inch Ruhmkorff coil, which meant you could have a gap here of 42 inches or a little over a meter and generate dielectric breakdown of the air. And in that coil, they used 280 miles of wire. Now, when Heinrich Hertz demonstrated the existence of electromagnetic waves, he used a spark coil to launch his electromagnetic waves. The name ignition coil comes from the use of these in automobiles, where your ignition coil will have a primary with 150 turns and a secondary with 15 to 30,000 turns. And in your car, it will take your 12-volt battery and generate voltages on the order of 15,000 volts applied to a spark plug to get a spark and ignite the fuel mixture. What we're going to do is describe spark coils, explain how they operate, and we will build and demonstrate one. In a spark coil, you have two coils. You have the primary coil, which will have the smaller diameter, and then the secondary coil with the larger diameter, and the primary fits inside the secondary. And in a car ignition coil, you'll have on the order of 150 turns on the primary and 15 to 30,000 on the secondary. So the secondary will have many more turns than the primary. We start with a material that has a high permeability and a low conductivity. The high permeability will mean we'll be able to generate very large magnetic flux density fields, and the low conductivity will mean we won't generate eddy currents when we have a changing magnetic field with respect to time. Now, around this material, we will wind the primary. So here we have the primary wound around it, the material, and it's attached to a battery and a switch. So when we close this switch, we will get a current flowing through the primary, and we will generate a large magnetic flux density field inside the primary. So here we have the switch closed, the current flowing, and we have our large magnetic flux density field. Now, if we open this switch, we will abruptly stop the current, which will cause the magnetic flux density field to collapse. So we'll get a large change in magnetic flux with respect to time inside the primary. Now, around the primary, we are going to wind the secondary. Here we have the secondary wound around the primary, and we have this spark gap in our secondary. So when we close the switch, we get a current flowing through the primary, causing a large magnetic flux density field inside the primary. When we open the switch, the current stops and we get an abrupt collapse of the magnetic flux density field inside the primary. So we have this very large change in magnetic flux with respect to time inside the primary, but it's also inside the secondary because the secondary is wound around the primary. So the change in flux linkage with respect to time associated with the secondary is the number of turns of the secondary times the change in magnetic flux with respect to time because of the opening of the switch in the primary. So in this way, we can take a low DC bias, in the case of your automobile, that would be the 12-volt battery, and generate voltages on the order of 10 to 20,000 volts, which is large enough to get a spark across this gap, igniting the fuel mixture in your car. These coils take a small DC bias and generate very large voltages, so they can be extremely dangerous. Even a small coil with a 1.5 volt battery can deliver a strong shock. I am going to show the construction and operation of a spark coil because I think it helps to clarify the concepts for you. But unless you're an expert in working with high voltages, you should not construct one of these coils. I have these ferromagnetic strips that have been coated with an insulator, and I have 26 such strips here. And I'm going to take them and stack them. And these are going to form the core of our spark coil. So I have a piece of plastic here that will be used to hold them in place. Okay, so the ferromagnetic material has a high permeability, and the insulator between each of these strips causes a very low conductivity, so that when there's a changing magnetic field, there won't be large eddy currents generated inside this core, which would lead to power loss due to I²R heating. Now what I'm going to do is take this wire here and wrap it around the core to form the primary of our spark coil. I have now wound the primary around the core, and it consists of 300 turns. In a typical car ignition coil, the primary would have about 150 turns. Now, I have this plastic tube that this primary assembly will fit into, and so now around this plastic tube I'm going to take a second wire and wind the secondary, and the secondary is going to consist of 30,000 turns around this plastic tube. Here is the completed secondary, and it has 30,000 turns, and our primary can slide right inside the secondary. I have the secondary connected to our spark gap, so this would in a car be represented by the spark plug. Now the breakdown strength of air is 3 million volts per meter, and I have a gap here of about a half a centimeter, so in order to get breakdown of the air in that gap, I will need to generate at least 15,000 volts across that gap. So over here I have the primary connected to a 9-volt battery. So I'm going to take this 9-volt DC battery and generate 15,000 volts. So the battery feeds the primary, and in one leg of the primary I have this switch. Now this switch is closed when it's pushed in and opened when I let off on the switch. So when I push on the switch, I have a current flowing through the primary which will generate a large magnetic field. And when I let off on the switch, there's an abrupt stoppage of the current and a collapse of the magnetic field and magnetic flux. So if I take the primary and insert it into the secondary, when I stop the current and get the large change in magnetic flux with respect to time inside the secondary, then that change in magnetic flux with respect to time is multiplied by the 30,000 turns I have to give the change in flux linkage with respect to time associated with the secondary. I will now repeatedly close and open the switch in the primary, turning the current on and off in the primary, and taking our 9-volt battery and generating a voltage at least of 15,000 volts across this gap so that we get dielectric breakdown in the gap.